Welcome to lecture 17. So, in the last class we talked about Huffman code so how does it work? So suppose you have some symbols and these symbols can be some voltage value. So when I am writing the alphabet to be say A1, A2, A3, etc. up to say AM. So in reality it means that after quantization these are some values. So this alphabet can be say minus 4.5 volt, minus 3.6 volt, etc. minus 2.4 volt, say 0 volt, 2.5 volt, 3.5 volt, 4.8 volt, etc. So these are some typical values, like you apply some quantization rule and these are the so-called representative points. So A1 to AM. So like you learned about the Max-Lord algorithm, right? So you know how to choose that number capital M. So now that is again coming from information theory, of course, the differential entropy and the the mean square error. Now you have you know the probabilities, because the probabilities are also coming from that quantization. So once you know the probabilities, you have those P1, P2, etc. You know that how to apply Huffman algorithm to get the code ready. So Huffman algorithm will give you the corresponding code. So for example, this I have 4, say A1, A2, A3, A4. The alphabet is this with some probabilities, say 0.5, 0.2, 0.2, 0.1, something like that. So I assign some code. So the code is say A1 is say 0, A2 is say 10, code A3 is say 110, and A4 is say 111. This is the simplest Huffman code possible. So you can see the tree is like this: 1 0 1 0 1. So these are for A1, A2, A3 and A4. Now this tree or this code assignment, which is in this tabular form, I call this the code book. The code book should be available to both the transmitter and the receiver side. So it is like your like signal source. So your signal source which is a random process, which is generating random process, and I am including the sampler and quantizer within this. So then it is passing through the encoder. So the encoder is doing this, that the input is coming to be these values which are coming out of the quantizer, and the encoder is assigning these values. So suppose the signal source is emitting some values like say A2, A2, A1, A3, A1, 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 F4, etc. So if that is the sequence of values coming out of the signal source after quantization, the encoder will assign based on this code book the corresponding bits. So the bit sequence will be for A2 it will be 10, for A2 again it will be 10, for A1 it will be 0, for A3 it will be 110, for A1 it will be 0, for A1 it will be 0, for A1 it will be 0, for A4 it will be 111. So this sequence will come out of the encoder. So encoder does not know about the exact values the alphabet assumes, because I really do not demarcate whether these are some volt or some real number or some really abstract values. So these can be abstract symbols as well. But when I am assigning the code book means for every symbol that can be abstract symbol as well, I am assigning a bit string. So for every symbol there is a string of bits, and finally the encoder output will be this only. Now the decoder, there will be then channel and everything else. So I am assuming everything to be a channel. Say this is a discrete or digital channel. Then this is the receiver side when it has to pass through a decoder. So this encoder and decoder is like a couple. So for whatever this encoder does, the decoder does just the inverse thing to get back the symbols. And this process is without any loss. So you should be able to regenerate, to recover everything from there. So if the channel does not include any noise, and if the channel does not corrupt this sequence, and if the decoder receives this sequence, the decoder should be able to get it back, get the symbol sequence back. Now for this, the important thing is that the synchronization. You should know that what is the starting point. So from where you should start. So if this is the starting point, A2 is the first symbol. Here also there should be some synchronization mechanism. We will talk about that later when we talk about estimation. But of course there should be some synchronization mechanism. And if there is some synchronization mechanism, if we know that what is the starting point, then from the prefix tree encoding scheme, which is the Huffman encoder, we will be able to decode it immediately. For example, when this is coming, so immediate first bit is 1. So just observing this from the root, you see which direction it is going. So you should have this tree at your hand at the decoder side handy. So whenever you see that 1 has come as the first bit, that 1 means you traverse this path. That is the 1. Next is 0, so you traverse this path. And you immediately hit to some leaf node, that is A2. Immediately you write that, okay, I reach leaf, so here I get A2. And that's why it is called like instantaneous decoding. Means whenever the corresponding symbol is the final bit, the LSB is received, detected, you can immediately find out that what is the corresponding symbol. So after receiving 0, you know that this is A2. And whenever one symbol is received, immediately you reach to the root node. So immediately you reach to root node again, then see what happens. What bit has come? 1. So again move this side 1, then 0, again 0. So you reach again A2. So here again A2. So parsing parse is not required. Like you do not need any comma or full stop or anything like that. So the kind of prefix tree code that is good enough to find out that when the symbol has been reached, the symbol has been received. So 1 0, A2 has been received, then 0. 0 means immediately you come to A1. So here you come to A1. Then 1, 1, again 1, then 0. So A3. So 1 1 0 is A3. Next 0, A1. Next again 0, A1. Next again 0, A1. Next 1, 1 here, then another one here, another one here, A4. So this is A4. So you see this sequence is received after the decoder, and this is exactly same as what has been sent from the signal source after the quantizer. So that is A3, A2, A1, A3, A1, 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 A4. So this is how Huffman encoding works. So the tree by which you are generating the coding scheme, that should be present both at the encoder side and the decoder side. And this is essentially a simple if-else loop, if you can think that a binary tree that can be represented using a computer or a digital circuit pretty easily. So this is essentially the tree is represented at every node. This is some if-else statement. If 0 this, else this 1. So this is essentially if-else. And from a digital circuit point of view, this is nothing but multiplexer, right? Mux. You know Mux. So Mux is basically a 2 input 1 output system which is controlled by some select. So you know that if mux and demux, so encoder it will be mux, at the decoder it will be demux. So if 0 and 1, so based on the selection it will pass either 0 and 1. There is a switching mechanism which is like the if else. So I am not talking about this circuit as of now, but you think about it because you know digital electronics, and if you have any specific question about designing this encoder, suppose this is known, this graph is known, how to design a encoder circuit, that you please tell me, and similarly the decoder circuit. Okay. So now let us proceed towards the Markov source, because till now this Huffman encoding we discussed only about the discrete memoryless source, which are every random variable are independent and identically distributed. So my distribution is for that IID like discrete memoryless source. But if you have Markov source, then also we can apply Huffman encoding, but we have to do it in some intelligent way. So let me tell you quickly how to apply for Markov source for a stationary source, and we know that any stationary source can be modeled as Markov source. So Markov source, it should have, so for every alphabet, suppose A1, A2 to AM, there should be a transition probability matrix. Some transition probability matrix. And this transition probability matrix is given by basically some probability values, say Pij, which is equal to basically probability that the previous state, the current state, if the previous state is I, so I can say x at k plus 1, the k is time, say k is the times time points, discrete time, is I, sorry, the previous time point k is I, then x k plus 1, that next time point will be j. So this probability, and this is for all I and j. I, j is equal to 1 to m. K is the time point. So these probabilities should have these following characteristics, that Pij for all j is equal to 1 to m should be 1. So every row vector should be summed to 1, because these are essentially the conditional probabilities, and they are essentially probabilities. Previous state is I, that's it. Then the scheme is as follows, that if you do not know the initial distribution, suppose if you don't know the initial probability state distribution, state probability distribution, then how you can start? You can assume that at time t is equal to 0, say k is equal to 0, encode the states. States means basically the symbols, using fixed length. Encoding. So you have to use log m bits per symbol, and this should be known. So you have 000001010, etc. So this is regular binary encoding, okay, fixed length encoding. But once that is done, then assume that you receive some signal, the first bit, first symbol. So x at time t is equal to k is equal to 0 is, say, ai. That is the first symbol received, and for this you use log m number of bits. First symbol received. Then what you have? Then you know the probability distribution, and using this probability distribution for every I, you have Pij for j is equal to 1 to m, that is like a PMF for the next state, and using those, so Pij, using these, j is equal to 1 to m, using Pij for that particular I, design Huffman. Okay, and you encode it, and based on that particular graph, that particular tree, you encode the next symbol and send. Now that symbol can be some k, some other j, and for that j again you have the corresponding p, j, l or something. Using that you again design some Huffman. So essentially from this transition probability matrix, every row should have a different Huffman tree, and for every row you should have a different Huffman encoding. So I'm giving you one quick example, that then it will be much more clarified that how you can go for Huffman encoding for a stationary or Markov source. So I'm taking, say, alphabet with 5 symbols, say A1, A2, A3, A4, A5. So for 5 symbols, my transition probability matrix will be 5 cross 5. So this is A1, A2, A3, A4, A5. A1, A2, A3, A4, A5. And let us assume some values. So the values are, say, okay, this one is, say, uniform, 0.2, 0.2, 0.2, 0.2, 0.2. This is some skewed, suppose 0.5, 0.2, 0.2, 0.05, 0.05. This one is, say, 0.4, 0.4, 0.15, 0.03, 0.02, something like that. This is, say, 0.6, 0.1, 0.1, 0.1, 0.1. This is a 0.4, 0.2, 0.1, 0.02, 0.18, sorry, 0.08, something like that. Okay, this is some transition probability matrix. Oh, okay, let us change this to 0.1 and this is a 0.6. It does not matter. I put in a particular way, like non increasing kind of way, but that need not be the thing. Say this is okay, fine. Now for every row, you check that every row is sum to 1. So every row is a legitimate PMF. So the first bit at time t, k is equal to 0, k is equal to 0, you have fixed encoding. You have fixed length encoding, fixed length code. So you code like this: A1, say 000, A2 001, A3 010, A4 011, A5 say 100. This is regular binary encoding. Okay. Now based on that, now whatever has come to your like decoder, or based on the observation from A1 to A5, you have to have 5 different Huffman table. So Huffman table for all past values. So Huffman table for, say, x k is equal to A1. Then you have to design Huffman table, for, or Huffman tree for xk plus 1. xk plus 1 to encode xk plus 1. How to do that? So you take this first row. So first row, probability of aj given a1. This first row is basically 0.2, 0.2, 0.2, 0.2, 0.2. Uniform. So if this is uniform, I know that I cannot help, but even if you apply Huffman, it will be 3-bit. So let us see how does it work. So I can write here. So this is, say, 1 0, so 0.4 will come this side, and this to, say, 0 1, this will come here. So this is 0.4, 0.4. I'm writing only the probability. Okay, this is like shorthand, and this is like 0.2. Then you merge these two. This is, say, 1, this is 0, and it will have a probability of 0.6, and this is 0.4, and merge finally these two. So this is, say, 0 and this is 1. So I can see clearly that A1 will have the encode. A1 will have it will have 0 1, 0 1. A2 will have, you do it yourself, then only you will understand clearly. A2 will have, this is A1, this is A2, this is A3, A4, A5. This is the next next symbol. A2 will have 0 0 0. A3 will have 0 0 1. A4 will have 1 0, A5 will have 1 1. So that's the tree. That's the tree. So here tree I can, like this tree I can redraw in this way. So from this side 0 1, then 0 1 0 1 0 1 0 0 1 1 0 1 1. You see, contrary to the fixed length encoding where you use 3 bits for everything, here for 3 I use just 2 bits, and for 2 I use 3 bits. So here this is my A1, this is my A2, this is A3, this is A4, this is A5. So if I have this chart with me, then suppose a symbol comes, the first symbol is 0 0 0 out of the encoder. So this is my encoder. Encoder emits 0 0 0. So we know that the first symbol is essentially, so the decoder should understand there is some channel inside, and this is my decoder. So decoder should understand that 0 0 0 means A1 has arrived. Okay, this is at time k is equal to 0. Now once the first bit is A1, after that if you have another 0 0 0, suppose, now this 0 0 0 is different from this 0 0 0. The first 0 0 0 is A1, that is the fixed length encoding at time k is equal to 0. That's why synchronization is important, because the same symbol, the same set of bits will give you different symbols. So the first 0 0 0, when you are using this fixed length code, this 0 0 0 means A1, but previous symbol is A1. If the previous symbol is A1, then the next 0 0 0 is A2. Next symbol is A2. Now since the next symbol is A2, you have to generate another Huffman code for the second row. So you should have 5 Huffman codes. Let me quickly show you what they will be. So for if the previous state is A2, then the probabilities are 0.5, 0.2, 0.2, 0.05, 0.05. So I can write 0.5, 0.2. I am writing like horizontally. Here I have written vertically. Horizontally I can use the space in a better way. 0.05, 0.05. So clearly these two will combine. This will be 1, this will be 0, and sum is 0.1. Here 0.1 is smaller compared to the others. So this is 0.1, this is 0.2. So these two will combine next. 0.1 I am writing here. So these two will combine next. So this combination is 0.3, and here I am putting 1 as code here, 0 as code here. This 0.3 will go up, 2 will go down. So these two will combine next. This is 1, this is 0, and these are 0.5, 0.5. So 0.5, 0.5 will combine next, 0 and 1. This is the total probability. So the tree is essentially 0, 1 1, 1 0 0, 1 0 1 1 0, 1 0 1 1 1. So A1 is essentially 0, A2 is 1 1, A3 is 1 0 0, A4 is 1 0 1 0, A5 is 1 0 1 1. So this is the code for that. So after A2, if the signal appears to be say 1 1, then you have to understand that this 1 1 is essentially A2 again. You see, so here 0 0 0 means A2, next 1 1 means A2. So this is how you should proceed. So I am asking you that you generate the Huffman code for all of them, and then this is like your small homework, you try. So for this particular like Markov chain, you try this sequence: A1, A2, A2, A4, A1, A5, A1, A2, A3, A4, A5, A1, A2, A2. So this is the sequence, suppose, which has arrived out of the Markov chain. So you using the Huffman encoding, you generate that Huffman code for all the rows, and you find out the bit stream for the given Markov chain. And since this is this is the time t is equal to 0, a1 you encode using the fixed length encoding. Okay. After that, everything should follow from different rows. So for a2, for the second one, it will be a2 given a1. So a2 given a1 will come from the Huffman code of this row. a2 given a2 should come from this row, the second row. a4 given a2 should come from again the second row. a1 given a4 should come from the fourth row. a5 given a1 should come from the first row. a1 given a5 should come from the fifth row, and so on and so forth. So for every row, for the 5 rows, you create 5 tables, 5 trees and the 5 tables. So these tables will give you the symbol to code like map when previous state is, say, this is a2. So x k is a2, and this is for x k1, k plus 1. Here it was for previous state is a1, here a2. Okay, do for a3, a4, a5, and then prepare the bit stream for the entire thing. Then using the same thing, you decode from the same charts. You should decode, because the decode will follow the same suit. You should get back this particular stream. Okay, so this is Markov source. Now I will use Huffman code does not use information theory, so that is something good, of course, but it relies heavily on the probabilities. So that is something bad, because the probabilities are difficult to estimate some of the time, but information theory is more of like a statistical behavior, statistical characteristics, although the definition of entropy itself depends on the probability. But once you know the entropy, I do not care about individual probabilities that much. That value will guide me, the corresponding entropy value or entropy rate value or whatever value should guide me. Oh, okay. In this Markov example, do another thing. For this Markov chain, compute entropy rate. Okay, what is entropy rate? I have taught already. So find out the entropy rate and compare that entropy rate with the bit rate you find out from these symbols, with the bit rate, the experimental bit rate you observe from this like small homework from this sequence. So what will be the bit rate you are getting? So essentially how much time it is: 1 2 3 4 5 6 7 8 9 10 11 12 13 14. So it will be basically 14 millisecond, you can say. So this is 14 milliseconds. So one symbol per 1 millisecond. So in 14 millisecond, how many bits are required? So when you find out the bit stream, you find out that how many bits are there. So many bits divided by 14 milliseconds. That will be your bit rate in kbps. Millisecond will become kilobit per second. Compare that with the corresponding entropy rate. Compute it from information theoretic understanding. Okay. Next, I'll move towards. Let us take that inequality of entropy. I am going back to again DMS, a discrete memoryless source. Suppose you have a discrete memoryless source, and I know the source coding inequality, which is hx is less than the average length is greater than hx plus 1. Now we have understood that if you try to find out the the code from Kraft inequality, the problem which problem which happens is that the corresponding probability values, and when you are trying to find out the length using this equation, there is lots of redundancy which you are still leaving here, such that this hx plus 1, this is not really a tight bound. When you can work with, say, some L is equal to, so let us take some typical value. Suppose hx is equal to 2.3 bits. So hx plus 1 is actually 3.3, right? 3.3 bits. So my interest is to move my average length or the mean length towards 2.3. So if you find out some 3, that is not good enough. So it is possible to do 3 bits per symbol using simple fixed length encoding for many cases. So suppose there are a total number of symbols, so the cardinality of the alphabet is, say, 7. So you can easily do using 3 bits per symbol. So hx plus 1, 3.3 is not really helping me. Okay, what we can do, how we can use this? So instead of taking one symbol at a time, what you can do, you can group symbols. So instead of taking one symbol, if you take vector of symbols, so instead of x, you take xn. Xn is basically a vector of n consecutive random variables. So it is like x at time t is equal to 0, x at time t is equal to 1, up to, say, x at time t is equal to n minus 1, something like that. Okay, so if I take this vector, so this vector will belong to the space, this is basically the Cartesian product of the alphabet n times. Okay, so how many number of choices this particular vector is having, what is the cardinality of this particular vector space? So every random variable can assume one of the values from the alphabet. So the total number of such sequences will be obviously the cardinality of cardinality x to the power n, because the first random variable can take cardinality of x values, which is m, basically m to the power n. So this is the total number of such possible sequences. Now if I want to apply, so what is the total entropy of such sequence? If it is DMS, discrete memory resource, the entropy will be, so h of x to the power n is essentially nhx, because every random variable is independent. So it's like, if I draw graphically, they are non-overlapping. These are the Venn diagram. This is the Venn diagram. So this is, say, hx0, which is hx. 0 is time. This is also hx, and they are non-overlapping, so they are additive. Information is additive, entropy is additive. So this is an hx. Okay. Now, if I apply some craft encoding, which is called sometimes Fano encoding, Fano also, or Fano-Shannon encoding. So if I apply that encoding, and if I get the inequality, source coding inequality like this, so for that n tuple, for that n vector, if I compute the corresponding joint probability distribution, so p x1 to xn, these are the values, so this is the PMF, joint PMF, I can say, then I know that I can find out the length using this. So for this n symbols combined, I can represent that using a code whose length will be, so length, say L, I'm naming this event to be Li of some x to the power n. So that's like one instantiation of the vector. So this will be minus log pi of that xn, of that n vector. In this way you can do. Then the corresponding inequality will be the average for that ln. It will have the following inequality, that is h x to the power n and h xn plus 1, the same thing. Now hxn is nhx, and this I can think of that this is basically the average length for n symbols. So this is essentially n L, if this is for one symbol, this is equal to nhx plus 1. So combining n symbols, what I am doing, I am basically everything will be multiplied by n, but this one will be just 1 because that's coming from the ceiling thing. So now if you divide everything by n, you will get the modified inequality in this plus 1 by n. So making n appropriately large, you can tighten the bound. So you can have the upper bound pretty tightened, and you can enforce the average length per symbol to be close towards hx. So this is one way of doing it, but what is the cost? Why don't we actually take this approach for n really large? That's basically hardware, because you have to store the data for n such random variables, and then you have to have a table, Huffman table, which is for cardinality m to the power n. Suppose m is 6 and n is 100, so it will be 6 to the power 100. So like 7 to the power 100, suppose n is 100. So to have the accuracy of 1 by 100, which is like 1%, you should have a table which is having size 7 to the power 100. And what if it is not 7, it is say 128, so 128 to the power 100. So that's pretty big, and to store that data in the hardware in a digital circuit, that's not really convenient. So this kind of group approach, even though theoretically it is appealing that you can really bound it, in practical we don't use that often. But this gives me some clue that okay, if we take n random variables together, probably we can do better. And next, what I'm trying to do towards that universal encoding, which will be table free in one sense, we will move towards that. But for that we will need some more information theoretic results. So which I'm starting next, which is called the asymptotic equipartition property, and using this we will generalize the source coding techniques. So we will go towards universal codes. So one example is the most famous example is basically the Zib-Lempel encoding, which is used even today in computers, those compression algorithms. Okay. So please give a thought on this, and please give a thought on this, the assignment which the homework which I have given. Please try it out, because you will learn many things. Okay. So the next thing which I am starting today is the asymptotic equipartition property. This is essentially the information theoretic analog of the weak law of large number. I can say this to be the information theoretic analog of weak law of large number. Okay. So what is weak law of large number? Quickly. So suppose you have a random variable x, and you have some random variables x1 to xn, suppose n different random variables, and all are IID. So IID means independent and identically distributed. Independently and identically distributed. So our like source output, our quantization output, those random variables you can assume to be, if that is discrete memoryless source, you can assume them to be independently and identically distributed. All are having the same PMF and they are independent. Markov will be different. Markov is not independent, but DMS are independent. Then we know that the sample mean 1 by n summation or this sample the mean of those random variables, I can write this mean of those random variables k is equal to 1 to n. So this is also a random variable, but we say that this in probability this converges towards a constant. So the distribution of this becomes like a step function, and which is the expectation of x. So in probability, what is the exact statement? Exact statement is probability of 1 by n summation xk, k is equal to 1 to n. Capital X means this is the random variable itself, okay, minus expectation of x, which is the common mean of all of them, this greater than some epsilon is less than some delta. It goes to 0 as you increase n. So for large n is greater than some n0 as a function of epsilon, I can say. Delta is some small number. Okay, so this is the exact statement of the weak law of large number. This we have proved earlier, so I am not going into that proof again. But what I want to do, I want to like generate the asymptotic equipartition property. That is essentially like we will apply this result on the joint distribution of n random variables, and we will relate that with the entropy of the random variable. Okay, so suppose this x is the random variable. X is the random variable, which is basically the output from the quantizer. So this is your or digital source, I can say. So your digital source, which is basically generating, digital source means source followed by sampler followed by quantizer, and this is giving you the random variable x. This is prior to the encoder. The random variable is coming out. Okay, so if this is a random variable, the probability of x, which is essentially the PMF, right? So a random variable is what? Random variable is basically a map from the probability space to the real line. So this is a discrete random variable, means it assumes some value on the real line, and those values are like those a1, a2, a3 up to am. These are the values this random variable takes, right? That is the alphabet. a1 to am, those are the values the random variable takes. Now think of a problem like function of that random variable, which is px. P is the probability. So we know that every value of random variable is having a corresponding probability. So this x, the PMF basically tells you that x will be a1 with probability p1, x will be a2 with probability p2, p3, so pm. So these are some probabilities. So I can visualize that px is also a random variable which maps between 0 and 1, and it takes values. This px takes values p1, p2, p4, pm, etc. So these are the values the random variable takes, and such that the sum of them will be 1. So px is also a random variable. And if x, all x's are IID, then the corresponding px's are also IID. So if you take two instances of the random variable at two different times, x1 and x2 suppose, so px1 and px2 are also IID, obviously, that we know. So now this is basically a function of a random variable which is also a random variable. We are not stopping here, we are taking another function of this px that will also be a random variable. Suppose from here, so from here I am mapping to here. Now from here I am taking minus log of that. So it will take some values. So the values will be between 0 to infinity. 0 to infinity. So when some probability value is 1, then it will be 0, otherwise it will be large. So you take minus log of px. That is also a function of a random variable. Px is a random variable, minus log of that is a function of a random variable, which is also a random variable. And if they are IID, then they are also IID, then they are also IID. Okay. Now on this random variable, I apply weak law of large number. Then see what happens. Okay. So on these random variables, these minus log pxs, minus log px1, minus log px2, and minus log pxn, on that I will apply the weak law of large number. These are the different instances of the random variable. One is basically time. I am writing like this. It is essentially time. I did not use another set of parentheses, but this is essentially time. How many times you are drawing that random variable from the source. N instances. So this is basically the n tuple. Then since they are IID, I know that minus 1 by n log the joint probability of x1 to xn. This is the joint. This is the joint probability. And since x1 to xn are independent, this can be written as minus 1 log px1 into px2 into pxn. Isn't it? Now log makes it additive. So minus 1 by n summation log pxk, k is equal to 1 to n. Isn't it? Now what is this? This is essentially the average of some random variables. These are random variables minus log pxk, and you are taking the average. So it should, in probability, move towards the expectation of that. So it should move towards, as n tends to infinity, or I can write in probability, it should move towards expectation of this random variable. What is that? Expectation of the random variable. This is basically summation pxk log pxk with minus sign, k is equal to 1 to m, which is hx. Isn't it? This is small xk. This is the values it assume. Okay. So this is the expectation, which is the like hxk, which is yeah. I should write something else. J. Suppose j. These are the values. So this is the this is the entropy of x. So I see that this joint probability, log of joint probability, that is basically approaching in probability towards hx. What is the significance of that? What does this mean? This means you see what is happening to the joint probability. What I can say about the joint probability. So in some sense, the joint probability is moving towards x1 to xn. This is moving towards minus nhx 2 to the power of that. And hx is a constant. So minus nhx is a constant. So 2 to the power minus nhx is a constant. So the joint probability is like becoming a constant. So it is like becoming some uniform distribution. So when you are taking n random variables, the joint probability is becoming uniformly distributed. And if this is uniformly distributed, it will take like assume the entropy to be maximum. And if it is uniformly distributed, then you don't have to do any like Huffman encoding. You can simply do like fixed length encoding, and that is good enough, isn't it? So this will give us some clue about how to approach encoding from a different point of view, and it will tell us about that which sequences, when you take n random variables, which sequences are more likely to happen, and we will define the typical set based on this. So when you are taking, so the typical set will be the next movement. So suppose you have the random variable and you take the random variable for n different times. So starting from x0 to xn or x1 to xn, these are the n random variables, and this n tuple which takes values from x to the power n. So what is the size of this set? The size is size of x to the power n is basically m to the power n. That is the size. Okay. Now out of this we define a typical set. And we name it the typical set to be A epsilon n. This is how I say the typical set with respect to respect to the probability mass function, the PMF, which is Px. Then for this is basically a set of sequences of the form x1, x2, xn, and they belong to this set. One of them. Okay, so there are such m to the power n such sequences. These are the values. These are the values which it is taking, basically a1, a2, etc. So x1 is basically belonging to this, which is a1, a2 up to am. So x1 is basically one of these, x2 is one of these, xn is one of these. Okay, we say that this sequence, which I can write as a small x to the power n, this is how I write. Small x to the power n is basically the n vector, which is the random variables take. So this is basically one typical xn is basically I can write one typical xn is basically say a2, a2, a3, a1, a5, a7, etc. And there are n such, this is a n cross 1 vector. Okay, so every random variable takes one of the symbols and this is the vector. Okay, we say that the typical set is a set of sequences of the form such that which satisfies the following property, that the probability of that xn, this is the joint probability. Okay, joint probability, this should be less than equal to 2 to the power minus n hx minus epsilon and greater than equal to 2 to the power minus n hx plus epsilon. So epsilon is a small number, where epsilon is a small number. So I basically restrict, I am not saying, because you see over there that the probability is approaching towards 2 to the power minus nhx, but it should not be equal to all the time, because this is in probability convergence, it's not true convergence. So it should be between two close values when epsilon is very small. So it should be between 2 to the power minus nhx minus epsilon and 2 to the power minus nhx plus epsilon, between these two. Then we say that the set is typical set. Okay, now if this is typical set, it should we will show you that it satisfies certain criteria. I can write a theorem based on that. So let me write down the theorem for a typical set. So if xn, which is equal to x1 to xn, belongs to that typical set, then the following are correct, following are satisfied. Number 1, hx minus epsilon, which is essentially the definition, is minus 1 by n p xn greater less than equal to hx plus epsilon. Okay, sorry, log, I did not take the log. So log 1 minus 1 by n log pxn, this is essentially the weak law of large number. This is essentially the definition of the typical set. Okay, second is important, that is the probability of the entire set, the typical set, it is greater than some 1 minus epsilon for some large n greater than n0. Okay, n0 epsilon I can say. Number 3 is the cardinality of the set. The cardinality of the set is 2 to the power n hx plus epsilon. So that is the upper bound, again for large n is greater than n0 epsilon. This is some upper bound of the cardinality. The cardinality of the lower bound can be also obtained. This should be greater than equal to 1 minus epsilon 2 to the power n hs minus epsilon. Okay, so these are some characteristics of the typical set, and based on these characteristics we can develop the encoding which is like kind of the universal encoding. I'll state that first. I'll like prove this theorem first, and I'll state that first, then we'll move towards the Zibbe-Lempel encoding. So I am stopping with the statement of this theorem now. In the next class, possibly tomorrow, I will prove this theorem first, and then I will say that how we can do encoding based on this typicality, and then we'll move towards Zibbe-Lempel. So till then, bye.